Today we're going to be looking at using Zebra for real. So we're going to be looking at the early stage design of a 14-story apartment block in southern India. This document that you see before you is available on the Zebra website, and I suggest you download it and read through it before you do maybe your first design using Zebra. It's quite similar to the UK office block, but obviously set in southern India. It's a residential situation and it's a cooling dominated rather than heating dominated climate. If we scroll down through the document, you can see that we start with asking some questions about the design and what we might be able to learn using Zebra. Obviously, we'll be able to find the energy consumption of the building, but we're also going to look at whether air conditioning is really needed, what might happen if the energy use and carbon emissions were to be radically changed, possibly by the occupants becoming richer and electing to use air conditioning, and what strategies might be used to offset this increase. For example, is it worth insulating the walls? We start off with a brief description of the situation. And I'll quickly scroll down through that, and we have a design brief. In this document, the text in blue is the information that you'll be entering into Zebra. You can use this document either as a tutorial or just as an example and read through it. It's up to you. Here's the building, and it's actually a building that's been built, so we're cheating a little bit here. By using a built building rather than just a design brief. But part of the reason we've done that is because we've got some measured energy data from this building. So we'll be able to see how accurate Zebra is. On the right, you can see the plan of the building, and you can see there's 4 interlinked accommodation towers together with this central lobby area. And in this piece of work, we're going to largely treat the center lobby area as not part of the building at all. So it's not going to be part of the treated floor area. And we are going to study a situation where we believe the temperature inside that central lobby is very similar to the outside, and also when it's distinctly different. And we're going to do that by considering the walls between the lobby and the accommodation blocks as either adiabatic, which means there's no heat transfer, and we're going to achieve that by setting their U value to 0. And we're then going to repeat the exercise, but with the U value of those walls set to the same as the external walls. And that will automatically link that those lobby walls to the outside air temperature. And that's called parametric modeling, when we take 2 possibilities of a situation, we're just not quite sure how to represent it. So for example, we might not know exactly how people are going to ventilate the accommodation. So we're going to repeat the modeling in Zebra with option A and option B, just to make sure that we understand how the energy use or other parameters change as a function of that input parameter. And it's a way to add a lot of robustness to your modeling. If we scroll down through the document, we end up looking at this table here. And this is the list of inputs that Zebra needs to run at complexity level 1. And by complexity level 1, I mean some detail within the spreadsheet as far as inputs and outputs are concerned. And in Zebra, we have 3 complexity levels plus a 4th for programmers. And those 3 complexity levels say something about how much knowledge you have about modeling, but also how far you are along the design. Do you know the precise values of the efficiencies of various items, or do you just want to use assumed defaults? And at complexity level 1, you only see a subset of the possible inputs for Zebra, and you also only see a subset of the possible outputs from Zebra. So you're not confused with too many tables. You mainly see graphs, for example. And if we scroll down through this table, we can see the list. So we've got a space heating demand standard we're going to have to apply, a space cooling demand standard. And this is all in the requirements sheet. So the first column there on the left is the sheet that you'll be communicating with in Zebra. Now, Zebra starts with you having to express a philosophy. This is very different to other modeling software, where you just go ahead and model, you come up with an answer, and then you reflect on that answer. Here, we kind of demand that you set out the environmental philosophy of the building. So what's the maximum carbon that you and the client are willing to emit over the lifetime of the building? What design standard are you trying to meet for space heating and space cooling? So for example, are you picking up on the passive house standards or any other particular low energy standard? Then we have to put in things like the treated floor area. We're going to change the cooling set point in this particular example away from the default, because we believe the occupants actually heat that, do not cool that building with a low set point. We're going to have to say where the building is, and that will pick up a weather file. We're then going to look at the wall area and the wall U value, and we're going to put the standard parameters in that you'd put in for any building thermal model, to be honest. What's the ground floor made of? What are the U values and things like that. We're then going to look at possible thermal bridge calculations that we might use within Zebra. We're then going to look at the glazing, and the glazing is quite complex. One of the reasons it's complex, or maybe the main reason it's complex, is the fact that if you don't get glazing right within a thermal model, you've really got a problem. For example, it's very common, it depends where you are in the world, but on a summer's day, there's often about 1 kilowatt of heat in the form of light hitting a square meter of horizontal surface. So on your roof or through a glazed window on the roof, for example, for 1 meter square of ground, you've got a kilowatt of energy. Now, you've got somewhat less than that on a vertical surface, the sun will be at an angle. You've also got the fact that glazing will reflect some light. But it's pretty clear the number of watts per square meter is likely to be very large. And if you don't get that right, then the energy consumption of the building will go completely wrong. If you assume there's too much light getting into your building, maybe the cooling load will be much, much higher than it actually is in a hot part of the world. And if you're in a cold part of the world, if you think there's more light getting into the building than there is, you're going to predict a low energy use from the heating system, and it ends up being a very high energy use. And things that need to be accounted for are things like whether the occupants use external blinds, whether the windows are recessed back into the building fabric quite a long way, and therefore there's a lot of shading from the head of the window. How much of the window is actually glass? It's very common for 40% of UPVC glazing to actually be plastic, not to be glass. And if it's not glass, it can't let light in. Other issues are things like shading from surrounding buildings and hills and trees. And that means that the number of hours in the day that the facade is actually exposed to daylight, direct daylight, sunlight, could be half of what you think it is if the building was sitting there on an infinite flat plane. Then we've got to describe the air philosophy within the building. Is it naturally ventilated, mechanically ventilated, and how many air changes an hour, etc. Now, part of that air calculation will be the average number of occupants in the day. And that really means the average over the hours in the year. So maybe the people are out of the building a lot of the time. So you don't want to be putting the maximum number of people that the building can hold or sleep in the building or something like that in there. You want to think about what the average occupancy density is. Then we look at incidental gains, and then we look at systems. And one of the unique things about Zebra compared with other simple models is, or even complex models, which can be run in a simple form, is we demand that you define things like the domestic hot water system, how much water people use, how much of the roof area could be used for PV. And the reason we do this is if you don't include the efficiencies of such objects, then you get a very poor prediction of the energy use of the building. And here you can see some more of those. Finally, we're going to input some thoughts on the embodied carbon. So that's the carbon that was emitted due to the construction materials being made, manufactured, transported, and then the building being constructed on site. So, for example, it covers all the energy use used to form the materials from which the building is formed. Zebra can be downloaded from the zebra-model.org website. There you will have the ability to look through lots of tutorials like this one, but also to look at documents that tell you how to do some of the more complex things in Zebra, and also download a new version of Zebra. It's mission critical that you download a new version for each new building you do. The main reason for this is that within Zebra there's lots of cells and lots of tabs, and there's a very good chance you won't clear out something from previous design, and that'll radically change whatever energy predictions you make, and they'll just be incorrect. So download a new version of Zebra for each new building. Another reason to do it is there's probably errors, bugs, whatever in any software, and that includes Zebra, and we'll be changing those. We'll also be improving some of the calculation steps, improving the functionality on a regular basis. So you want to be using the most recent version so you can get the most, the best results from it. But the main reason is the fact that you're bound to have something hidden in some cell. And we haven't given you the facility to clean out all the cells with a reset button, because we were advised by some of the companies that help us that they didn't really want a spreadsheet that included macros for reasons about viruses, etc. So we had to have a spreadsheet with minimum functionality in that respect. So there's no clear out button, and you need to download a new version of Zebra each time you use it. When you go to the download tab, which is here, you will see we'd really like you to enter a tiny bit of information. So something about your company or institution, something about the building, whether it's a school or domestic or something, and its approximate floor area and where the building will be built in. Okay, and the reason we're collecting this data is partly so we can look at where Zebra is being used and by whom, and make developments directed towards that direction. But it's also because we're actually really interested in how much activity is happening in the world with Zebra. So thank you very much for filling that in. It's going to be really, really helpful. After you downloaded your copy of Zebra, you need to open it, and I'm going to open it here. And you can see that there's a large pinky purple area, and whatever tab you go to, you will find an equivalent pinkly purpley area. And the pinkly purpley area is instructions. The reason I'm saying pinkly purpley is that on some people's screens it's purple, and some people's screens it's pink apparently. So it could be either with you. So you need to read these instructions the first time that you engage with Zebra, and you might want to refer back to them in subsequent use. They contain a mix of information. They contain information directly relevant to Zebra, so how we developed it, and what kind of inputs you need to put in, so the exact definition of air changes per hour or treated floor area, for example, so the numbers we're expecting to see in the boxes to get the correct answer. But it also contains a lot of tips on low energy design, so things about air tightness, and tips on modeling, why it's important to get certain parameters really well described and very precisely described, and why you can be a bit more relaxed on some of the other parameters. So first time you use Zebra, you need to read that purple area on each sheet, I'd suggest, as you fill that sheet in. On the website, you will find a document containing all of the purple areas just as a continuous Word document. And you can therefore, if you'd like and if you prefer, to sit down and read that more like a book or a report, rather than as an interactive thing as it is here, sheet by sheet. Along the bottom of Zebra, you will find a series of tabs, and they allow you to access each of the spreadsheets and put information about the building in with obvious, the title of the spreadsheet matches the information you're going to have to provide. So glazing allows you to describe the windows, for example. If we click on instructions, after reading the pink area, of course, you will find this piece of information here, this input cell. Now, the input cells are all in this yellowy beige color. Sorry for the my calendar still running. I can't seem to turn it off. You will find this yellowy beige type cell, and all of the input cells are of that color. So you're only interacting with the yellowy beigey cells. Other cells are just for information or results. Now, you'll see here this cell has the requiring you to input the complexity level. And the complexity level describes how much you want to see as far as the calculation goes, how much information you've got about your building, and how knowledgeable you are about modeling. Now, I've set the complexity level here to 1. I've got a choice. 4 is just for those wishing to add more functionality to Zebra, and will show an awful lot of numbers that most humans don't want to see. Level 3 will give you the maximum level of results and the maximum level of input information. Level 1, which we're mainly going to be using on this project, is what we would recommend if you're a first-time user or if you're at the early stage of the design. So you haven't got some of the detailed design aspects bolted down yet. So we'd normally recommend you start at complexity level 1. You don't need to start a new spreadsheet. If you want to swap complexity level at any point on any sheet, you can just come back to the instruction sheet and change complexity level, and then change it back again, which means that you can actually access some more complex functionality just very briefly. And we're going to do that in a minute when we look at changing the set point of the cooling, which is displayed at complexity level 3 and hidden at complexity level 1, uses the default of 26 Celsius, and we're going to change that to 30. But we're just going to go into complexity level 3 very briefly to do that, and then we're going to go back to complexity level 1 to try and keep the spreadsheets looking as simple as possible and to hide a lot of the extraneous information. We now navigate to the Requirements tab and bring up this spreadsheet. And here we need to state our philosophical environmental standard. Okay, so we start with the heating demand standard. Now, if you remember, we just looked at the document here that goes together with this tutorial video. And in here I had this table 1, which is a long list of input parameters needed to complexity level 1 to model your building. Now, I think it's best to try and assemble this table for each project before you start filling in Zebra. It's up to you. You can just open Zebra and you can just extract the information from your brain, from the drawings in real time, and just stick the numbers in. But this table here in the document, you might want to create a similar document in your own, in Word or on a piece of paper or something, and just fill it in about the design. It's quite good. You can sit down if you're in a group situation, in a meeting or a design studio project. You can look through this list and see how much of the information you know, and agree the values of parameters that you're going to use in the modeling. So I start with creating this table for every project. It then means I know I've got all the information that I need before I open up Zebra. Other people will want to just open up Zebra and start filling it in. Okay, but either way, make sure you read those pink areas of text so you have a full understanding of what the numbers actually are, and you're not assuming something incorrect about occupancy levels and things like that. So returning to Zebra, we see the first thing we've got to declare is the space heating standard. Now, you might want to use a very low energy standard like 15 kilowatt hours per meter squared of treated floor area per annum, passive house standard, or some greater value. Now, we're sitting in southern India, and we're going to assume that it's difficult to build a passive house. Probably none of the design team have done that. So we're going to double the default values used by the Passive House Institute. So we're going to assume zero heating for however, because we're in southern India. But for the others, we're going to use a space cooling demand of 30, so double what Passive House would suggest. That we're going to have to then say what the primary energy standard is. And primary energy is the energy used to make the energy that you need in the building, which sounds slightly confusing. But imagine that you're using electricity to cool or heat or run your building. And that electricity comes from a power plant somewhere. That power plant will have an efficiency. So it'll burn a certain amount of coal or whatever to create the electricity. And it'll do that with several inefficiencies, and it'll also transmit the electricity to your site with various inefficiencies, and we need to include that, and that's what's called primary energy. And one of the reasons we need to include a primary energy standard is, particularly in heated buildings, we don't want some designer faking the fact that it's a low energy building by assuming very high amounts of electricity use in the building. Now, Passive House have a maximum of 120 kilowatt hours per meter squared of treated floor area per annum. We're going to assume we can maybe design a building that is not so efficient, but runs at 240 kilowatt hours per meter squared of floor area. We've then got to say what the lifetime of the building is, and this is important because the embodied carbon will be factored across this time period. We're going to assume 60 for this building. And then we've got to think about the embodied and the operational carbon of the building. Now, best practice is about 500 kilograms of CO2 equivalent per meter squared of treated floor area. So that's quite a lot. So imagine you're building each meter squared, you've got half a ton of CO2 have been emitted in the manufacture of the concrete and the metal and the glass and everything. So we're going to go for best practice there and go for 500. Now, it's true to say Zebra is more of an operational energy model than a carbon model. So this is just going to be comparing the value against benchmarks. Whereas the operational carbon, so that's the carbon from the energy use of the building used to heat and cool and light it, which is at the heart of Zebra. It's going to calculate a much more accurate figure for that. And we're going to try and see if we can build a zero carbon building in southern India. So we're going to set that to zero. Zero operational carbon, that is. So we're going to have some energy use from the various systems, but we hope to offset that completely by the PV on the roof. This will actually be a huge challenge for this building because it's a very tall building. It's got a lot of floor area compared with the roof area. It's much easier with a bungalow to put enough PV on it to run the bungalow. It's difficult on a 14-story apartment block. We then have to define the floor area of the building. And we call this a treated floor area. It's the internal floor area, and it assumes certain areas can't be used fully by occupants. You can calculate a very precise value for it if you've got each and every room dimension minus internal walls, etc. And if you've got staircases, you can assume that people can't maybe use underneath the staircase. And if you've got services areas, it subtracts those as well. But the easiest thing is just to multiply your actual gross floor area by one of the values specified here, either 0.9 or 0.97. And for our building, I've pre-calculated it, which is why I like using that sheet beforehand, that table. And we've got 6669 meters squared of treated floor area. And virtually all the results in Zebra are reported with respect to treated floor area. And that allows you to compare the energy performance of buildings of very different sizes. So it's much better than using the total energy use of the building. And there we go, we've completed our first data sheet, the requirements sheet. Now navigate to the weather sheet. Here we see that we can choose a series of, we can choose a location for our building. Now, looking up the building's lat and long, and this is in table 1, so you could just copy it from there if you're actually just going to copy this building. It's 13.1, so not far north of the equator, and 80.3. Now, having done that, you will see on the right-hand side 4 possible locations from the building for the building, and by that I mean these are the locations of the weather file. So we're going to fake the building into one of these locations. Now, there's 3,000 weather locations in Zebra at the moment, but they're spread across the whole planet. So particularly with a country the size of India, you might find the weather station is quite a long way from where you're actually building the building. I mean, there's weather files for Delhi, for example, and capital cities by default. But if you're somewhere else, you might be a way away. So in this case, you are 159 kilometers away from the building, and there's nothing we can do about that. We then go to this box here, and into that box, we type our chosen location. And we're just going to pick the closest one. If you have more knowledge of the location and possible weather patterns, you might choose a different one. And we type that in. And that picks up Cuddalaw's weather information. You can also specify a temperature correction if you know the difference in altitude between where the weather station actually is and where the building will be. And if there's a large altitude difference between the two because of the adiabatic lapse rate, there'll be an offset in the temperatures between those two locations, and you can put that temperature correction in here if you so wish. We immediately see that we're displaying the outdoor air temperature, and this is the mean temperature in the month. So it's not a minimum and it's not a maximum, it's just the mean over 24 hours, 31 days a month or whatever. For that location. We also see the set points being displayed for our building, and they're the default ones because we haven't set any others yet. And on the right, we've got the solar irradiation with the main orientations of the building, so northeast, southwest, and horizontal. Now that doesn't include any shading from surrounding buildings or trees or hills. Okay, so that's just the raw data looking in those compass directions. But it allows you to think something about the time of year. On the left, you've got where temperatures are a maximum. On the right, for example, you can see that on the south facade, that actually the summer is the minimum irradiation. Is the time when the radiation is at a minimum. So this might help steer some design aspects or explain some of the results that we're going to see later. Now, as I said right at the beginning, we want to use a different set point, and we don't have access to that at complexity level 1. So we're going to quickly drop back, reset the complexity level to 3, go to the requirements page, set our temperature to 30 for the cooling set point, and then we can return to the weather page, and we can see that new set point has been replotted on the graph. And that's one of the great things about Zebra. Everything is immediate. You don't have a go simulate plot results phase, anything like that. You just get everything in real time. Now, so the sheets don't look so complex. We're going to drop back and reset that to 1, complexity level to 1. And when we go back now to the weather tab, you can see that 30 Celsius has stayed as the cooling set point. We next then go to walls and doors, and we've got to go through the major construction elements now: walls, doors, ground floor, roof, thermal bridges, the lot. Okay, so I quickly flip to walls and doors, and you can see here that we can specify up to 6 different walls, A, B, C, etc. And by a different wall, we you can use in this and in other parts of Zebra, like glazing. It's up to you how you split up and describe your building. So a wall could be a wall that points in a certain direction. It could be a wall on a certain floor. It could be a wall of a certain construction. So you could have 3 different external wall constructions. These are just external walls. And you could specify them and describe them in any way that you like. So we're going to return to the data that was in table 1 in the documentation that you've already assembled about the building, and start picking up values from there. We'll start with just naming the wall. So let's just do external wall. All our external walls are of the same construction, and we're not going to give details of its construction here. If you do, this will pick up U values and things for you, but we actually know our U value. So we leap straight away to our U value, and we type that in as 2.46, looking at table 1 in the document. Okay. And the area of the external walls, which we've worked out by hand, is 3905. We've then got the lobby walls as well to consider. So we put lobby wall, and the U value of that, as discussed earlier, we're going to set it as adiabatic, no heat exchange. We don't really know what the conditions are inside that lobby area. It's probably not as extreme as the outside conditions. It's sheltered in some kind of way, so the heat transfer will be different. So we're going to start that as adiabatic, and then we're going to change that later using parametric modeling. And the area of those walls is 1647. Okay. We then have lobby doors between the apartments and the lobbies, and again we're going to make those adiabatic, and we quickly need to look up their area from table 1. Lobby door area is 105.8 apparently, so whipping back into the spreadsheet, 105.8, and at the moment they won't have any impact whatsoever because their U value is 0. But once we go and have a look through parametric modeling about their possible impact and whether we've modeled it correctly, you'll see that their area will be important. We then switch to the ground floor. Our building is in contact with the ground, and that means that, again, a bit like the lobby areas, it's not exposed directly to the external climate. The temperature underneath the building will be some function of the climate, but it certainly won't be the same as the climate. If you dig a hole in the ground and put a temperature probe down, say 3 or more meters, the temperature you normally get to is virtually identical to the mean annual air temperature of the location. And something like that is happening underneath our building. However, around the around the outside of the building, so the ground floor slab that's much nearer the outside world, the temperature directly under there will be closer to whatever is happening in the outside air. It won't be the same. So we need to do some kind of calculation that says, oh, the building is not as exposed with reference to the ground, the ground floor, as if it was sitting on stilts, but some of it is more exposed than others, and might think, oh, that must be a complex calculation. Well, there's a standard for doing that, and we've captured that standard within the Calculators tab. So if I just flick through the tabs along the bottom of the screen there, and I visit Calculators, you'll see there's a whole series of calculators that help you do sub-calculations that might be useful in setting up the glazing, setting up, in this case, the ground floor situation. Now, no information flows directly from these calculators to any of the other sheets, which means you have to copy and paste anything you calculate here back into the sheet. And what that also means is there's no need to use the calculators. If you want to do a hand calculation or ignore something or include something else, you just do that hand calculation and you put your result onto the sheet of interest. Now, you'll see here we've got calculators on infiltration, thermal bridges, glazing, and we're going to come to that in a little while. But we've also got an area here. It's called ground floor static U values, and calculated according to these particular ISO. And to complete this calculation, we simply put in the U value that we think the floor would have if it was just treated as a U value in contact with the outside air, and this is 103 according to the table. We put in the area of underneath the building of the ground floor, and that's 529. Again, that's a hand calculation. We put in the perimeter, 184, so that's all the way around the outside of the building. And we have to make a guess at the wall thickness. And we're just going to guess a value here of 150. And this is a classic example where if you were unsure about something, you could make a guesstimate of what it might be, find your annual energy consumption of your building after you filled in all the other details, and then go and adjust this value, see what would happen if we went for 0.3, so 30 centimeter walls. Would it really change the effective U value? The ground conductivity, we're going to use the default value because we're stage 1 modeling here, early stage design. We just really don't know, but so we're using all the Zebra defaults, and that comes up with a adjusted U value of 0.4496, and you can see that's actually half the value roughly of the 1.3 we started with. So the fact that the building is in contact with the ground halves the heat transfer through the ground floor slab, as you might expect. And that's an example of something you've got to get right. If you don't get this right, then the heat transfer through the ground floor will be identical to the heat transfer through the roof, because they have the same area, if they had the same U value, unadjusted U value. So we can either just remember that number, or we can copy it electronically. Then we go down back to ground floor, and we're going to paste it in here. Okay, and when I paste stuff, it's really important when you copy and paste from the calculator sheet into any of your other sheets that you use the equivalent of edit paste special values, or you type it in by hand. If you just do copy and paste, you'll, of course, under the rules of Excel, not get the value, but you'll get the equation. And that equation will be pointing then, because you're copying it into a different sheet, to completely incorrect cells, and you'll just get rubbish. Okay, so you need to copy it by hand, just memorize it and type it in, or use copy paste special values. The area of the ground floor is, we know already, is 529. And then we turn to the roof. Okay, we only have one roof type, so we're just going to put roof in there. The area of the roof is also 529. And the roof U value, initially, we will change this later as we improve the design, we're going to put in as 4.2. Fantastic. We next turn to thermal bridges. There is a lot of text on the thermal bridges sheet, and it is worth you reading all of it to get a clear idea of the data you need to enter. Moving over to our orangey beige boxes and trying to fill those in, we get this. So the first thing you can decide is whether the building really doesn't have any thermal bridges. So if you've got a super insulated building with the insulation layer being 2/3 of its normal depth over all columns and everything, and there's no concrete lintels exposed to the outside temperatures or anything like that, you can probably declare the building as thermal bridge free. And that's when we're looking at low energy design in much of the world, that's actually what we're trying to do. We're not trying to specify accurately the number of thermal bridges. We're actually trying to design a building without thermal bridges. So you can just answer that question with a yes if you had one of these super insulated, well wrapped in fluff like buildings, which we don't have here. So we're not going to say yes to that. We're going to do something else. And we don't have enough design details yet to decide on how many thermal bridges we have, if they're point thermal bridges like wall ties and things, balcony supports, etc. We don't have enough information about linear thermal bridges either, so that's things like lintels, etc. So we're going to have to do a calculation based on some default settings. And within a procedure called SAP in the UK, we have a quick way of specifying the effect of thermal bridges throughout the whole building. And that requires us just adding up the area of the roof, the ground floor, and the walls, and then saying the mean impact of thermal bridges over those kind of areas will be a certain number of watts per Kelvin. And that's exactly what we do here. So we could use the default SAP value for the average scale of thermal bridges within UK housing. And that value is 0.2 watts per Kelvin per meter squared of surface area of the building. But we think maybe we can do a little bit better than that in this situation. It's a new building, so a lot of the buildings in the UK are quite old. So we're going to half that value. We're going to use 0.1 watts per Kelvin per meter squared of surface area. Now the total surface area of this building, so that's the walls plus the roof plus the ground floor, but without the glazing. Now we don't include the area of the glazing in Zebra when doing a thermal bridge calculation using the default SAP value, because the thermal bridges caused by glazing are more complex and we have a more accurate idea about what they might add up to, and we'll see that in the glazing calculation. So what you want to find is the surface area of your building without glazing. Okay, so find out the area of the walls, subtract the area of glazing from that, and then add to the result the surface area of the roof and of the ground floor. And whether you include the width of the walls in that will make virtually no difference, but whichever you like. Once we've done that, we multiply it by our coefficient, which is 0.1 in this case. And that gives our point thermal bridge coefficient, which would be is much bigger than it normally is, because we're adding up all of these thermal bridges into one big fat thermal bridge. So the surface area is 4963. So by the time we multiply that by 0.1, we're going to get 496.3. And the number of thermal bridges, we just have one giganormous thermal bridge. Okay. Once we've got that, we turn to the glazing sheet, which is the most complicated sheet to fill in, but we're going to use the most simple method for doing that. The first thing to do is to input the mid-pane U value. So this is the U value of the glass itself, or the glass unit, taken at the middle of the pane. So it's quite an optimistic value. And we put 5 in there because we've got single glazing. And that's what it said on table 1 that we set up earlier. And the G value is 0.85. And this tells you how much light is transmitted through the window, because glass isn't completely transparent. And you'll see on the right there's some default settings. We'd also put it in table 1. The glazing tab is the first of the more complicated sheets. So there's a lot of data here. And this first data table you can see is actually all the numbers that will go into the calculation. First piece of information to get your head around is that we have 15 window sets. Now, a large building can have an awful lot of windows, and it would take a lot of time to specify the details of each window in the building, its dimensions, etc. So we decided to have a shortcut, which is to allow you to specify up to 15 window sets. And a window set is a collection of windows that face in the same direction. But that's the only real connection between them. Okay, they face in the same direction. So we're going to add up all the area of all the windows on the on each facade, and we're defining a facade as those that point in the north, east, south, west direction. So we're going to have 4 window sets. We could split it differently. We could have a window set as being all the windows on a floor, or maybe we've got windows of very different type on different orientations and different heights and everything. So we could specify those separately, or we could just pick a particular window and define that as having its own window set, and then we'd be able to look at the heat loss and gains through that particular window. But we're not going to do that. We're going to go facade by facade, or orientation by orientation, and specify the area of window in each direction. Now, first thing to get your head round is, what do we mean by an area of window? What we actually mean is the area of the hole in which the window sits. Glazing will take up a smaller amount of space because there won't be a frame or any other glazing bars or whatever. But the default is to always start with the area of the hole. Now, you can see that there aren't any input cells there. There's no yellowy beige things. And they exist down here in this area here. And we need to specify this information for each of the windows. So the first thing we're going to have to do is work out the area of actual glass, the glazing area, from our hole area. And you can do that just by hand calculation, pardon me, or you can swap into the calculator, which is what we're going to do here. And we can either just navigate to the calculator tab and find where glazing is specified, or we've got these shortcuts, these little hyperlinks here. So you can just click on those and you jump over to the correct part of the table, which is over here, our shading calculator and our glazing calculator, which are all tables that we need for the glazing spreadsheet. So the first thing we do is think about how to specify the window and how much detail we have. So are we working with defined hole widths, frame widths, divider widths for glazing bars, number of vertical dividers, number of horizontal dividers, or not? And we're at a very early stage of the design, so we don't really have the windows well specified at all. So we're going to use a different technique, which is to look at these pictures here. And we have a series of pictures of possible windows that we might use. And you won't find the exact windows you were thinking of using, but hopefully you'll find something reasonably close. And what these windows are trying to provide a shortcut to is the fraction of the hole which is not glass. And we're going to choose window type H because we think that's best represents our glazing solution for this particular building. And you can see there that quite a lot of that is actual frame, quite a high percentage. And the percentages can be really high. If we just look at the type I next door here, and look at that top left window in type I, and if you were to run the maths on that, you would find that half of that fraction of the window is actually plastic, not letting any light. A similar thing exists over here on window type A. There's more wood in there probably than there is glass, and you've got to get that fraction right. So if you just pick the window closest to the one you think you're going to use, Zebra works out a rough estimate of the percentage of that window which is glass and the percentage which is frame. So we're going to pick type H, and we go below the photographs and we say it's going to be H. Okay. We then say the size of the holes, and we've added up, because we're talking about window sets here, we've added up all the hole areas. Okay. And on each elevation, we end up with 253 pardon me, meters squared of hole. And straight away, Zebra calculates the area which is glass, the area which is frame, the likely perimeter of those windows, and this rather confusing thing called length glass frame divider. That's a total length of frame and of dividers that subdivide the glazing units. And this is used in a thermal bridge calculation within the glazing sheet. Okay. The next thing we have to specify, and we know what we need to specify because it's always these orangey beige areas, is the permanent shading. And the permanent shading represents the all of the overhangs, all of the hills, all of the trees, all of the buildings in the local area with respect to how much shade they provide to a particular facade. And this number can be different on each facade. Well, it's different for each window set. So you could represent all your balcony windows in the whole building as a certain degree of shading or whatever. Here, we don't want to get into too much detail. It does explain how in Zebra, it does explain how to do a more complicated calculation, which is very similar to a daylight factor calculation, if you've ever done one of those. And we've provided a separate document on the Zebra website that goes into a lot of different ways about the 3 different ways we think you are best specifying windows within Zebra. From a very simple method like this, which is picking windows that look similar, to some quite complicated calculations. But you're unlikely to want to do those calculations till later in the design cycle, when you've really bolted down a lot more detail about the building. Now, we're going to use one of the recommended values in Zebra for this. And if we go to that orange red triangle, this is a general point. When you find a red triangle, go and look what the information that's stored in the comment box associated with it is. And we really think, if we look back at the actual form of this building that was in the original sheet, specifying it, look at that picture. Okay, it's some of these windows are incredibly well shaded from sunlight. And although they're actually on, it's not a particularly dense urban environment, but we do have sheltering from the buildings behind there and other blocks, for example, the one where the photograph was taken from. So this is a pretty heavily shaded building all round. The sun does not come up and start pouring light onto that facade first thing in the morning, because it's got to climb above the rest of the urban landscape. So if we look at the options here and we press that little red triangle, we see a value of 0.7 is suggested if we think it's heavily shaded by other buildings. So we're going to choose that 0.7 and we put in 0.7 there. And we've now specified the general form of our glazing for this window set. And we have 4 window sets. and they're all the same area, and they've all got the same shading and everything. So this is particularly easy in this case. And we then, either by hand, by writing the numbers on the paper, or by doing copy and paste, we copy these numbers. We go back to the glazing tab, and we go to window set 1, and we go edit, paste special, values only, and we get those numbers transferred. Or you could just write them on a piece of paper and type them in. We're going to name this the north facing windows, and we'll put north up here. Okay, we can have a whole bunch of different windows within a window set named if we want to break this calculation down. And we might have different permanent shading for each of those windows within window sets. So for example, you might have your window set might be all the windows that face north, or a particular window set, as I said, has to have a particular orientation. So these might be all the north way, but we might choose floors 1 to 3, floors 5, 6, 7, etc. as being separate sets. Separate windows, because we might want different shading. Obviously, the ground floors are going to have more shading than top floors. So we can subdivide this in quite a nuanced way, if you so wish. But at the moment, we're just trying to get our first estimate of the energy use of this building. Now, if we go further right, we've got to specify a few other things. And the first thing is the temporary shading and heating, and temporary shading, cooling. And we're just going to leave those blank, but we could put values of 0 in. And these represent the use of external blinds and shutters and things like that. So during the heating season or the cooling system, how do the occupants respond? You know, for half the day, are they likely to have these blinds drawn or not? We don't think people do use that technology in this location, so we're just going to leave those blank. The final item here is nRepeat, and that's explained in detail in the glazing document that I discussed earlier. But it simply says how many windows of this type do we have. So you can very quickly specify ribbon glazing solutions, and you can just have 20 of these windows. Okay, so you can either add up the whole area, as in the area of the holes, as we've done here, into 253, or we could have, if we had lots of identical windows, we could have just had a much smaller whole area and said there's 56, for example, windows of this form. Okay, so with that information there, all our windows are exactly the same on the 4 facades. So we just copy it down. And the glazing sheet really is the most complicated sheet. If you manage to get your head around filling in the glazing sheet, then the rest of Zebra will be trivial. And as we said right at the beginning, there's not a lot we can do to make this even more simple, due to the fact that you really do need to get your solar gains sorted and accurately specified. Okay. So north, we get this building is exactly aligned with the compass bearings, so north is going to be 0. East is going to be 90. But if your building was, rotated somewhat, you wouldn't have these direct ordinal directions. And that's our windows specified. So it is the most difficult part, but it wasn't actually too painful, we hope. And if we now scroll back up near the top, we'll see this glazing table, which is the information going to go into the calculation engine, has already be filled in for us. And we can just have a quick look at some of the numbers here. Because of all those frames and subdivision of the glazing from type H, you can see that only 75% of a window on average we believe is actually glass. So that's the first interesting fact. Okay, and we keep scrolling over to the right. Okay, the permanent shading is going to take out 70% of the direct sunlight pouring in through those windows on average, and therefore only 30% of the sky is visible. We haven't got any temporary shading, but if we just consider those facts, then only 13% of the light is getting into the building during the heating season and the cooling season that would get into the building if the glass was not recessed into the walls, if there were no surrounding shading objects, if the glass didn't reflect some of the value due to the G value. Okay, and there's a couple more of technical things which don't show at complexity level, but do show at complexity level 1, but do show at complexity level 3. But only 13% of the light is getting in if you hadn't made some of these more complicated assessments of the glazing. And this is why it's critical to get your glazing detailed correctly, even at this very, very early stage design. In a heating dominated climate like the UK, if you don't get this right, you'll end up with a building that suggests that it's self-heating just through solar gains. Okay, and if you don't get this right in somewhere like India, you'll end up with a building with a vast cooling load, which it doesn't really have. Fortunately, the air sheet is quite easy to fill in compared to the glazing sheet. Now, first thing we have to specify is how airtight the building is, and we're going to choose 6 air changes an hour. Now, this is 10 times more than a passive house would be, so it's quite a leaky building in that respect. But if we look at measured infiltration rates in common buildings, we can easily find values of 10 air changes per hour, 50 pascals. So this is during the pressure test when there's a big fan pressurizing the building. So we're going to go most of the way down from there, halfway down. So we're going to choose 6 air changes an hour, so 10 times the value of passive house. We then have to type in this red area, some justification. Now this cell actually doesn't do anything. It's just to ensure you write a note in there of some form. So if anybody else is looking at the sheet, they can see your justification for choosing this. The reason we've done this is we found a lot of people are over enthusiastic about the airtightness that might be realized on site, and they go, yes, we're going to get a really airtight building. And then when it's measured, it turns out not to be so. So we'll just type some notes in here that would justify it, maybe to a line manager or somebody else, or just to remind us why we chose this particular value. So we're going to write 10 times passive house value, therefore realistic. Okay, and you can see that goes from being highlighted in red to a more relaxing orangey beige color. We've already got the treated floor area in there. It's being ticked up from elsewhere. We now need to specify the volume of the building, the air volume. So this is all the air in the building. Okay, and we've worked that out by hand. We've got that value there. Then at this level of complexity, the only thing left to specify is the average number of occupants. And please read the pinky purple area about this and get a really good idea of what it is, because it doesn't mean the maximum number of people there's likely to be in the building. It means averaged over 24 hours, 7 days a week, 365 days of the year, what would be the average number of people in the building at any one time. And we've got some suggested values there on the right. They have been taken from information recorded in UK buildings, so they may not be relevant to this location, but they're the best guess we've got. And if we take the treated floor area and multiply it by the recommended value of 0.014 for homes we end up with 93.4. That's just a hand calculation, and we type that in. And we can see a whole bunch of information on this sheet now. The first thing we can notice is that we have the likely vent infiltration rate. So we have 0.42 air changes per hour wafting through the building, just from cracks in the fabric and around window frames, etc. It therefore takes 2.38 hours for all of the air in the building to be replaced just by infiltration. And if we were during a heating season or during a cooling season, that air is going to have to be heated or cooled. Okay, and you may know that the density of air is about 1 kilogram per cubic meter. So that's every 2.38 hours, 17,000 kilograms or 17 tons, because that's the volume of the inside of the building, of air will have to be cooled down if we've got cooling running. So this is actually quite a drain on the cooling system. We also can see the ventilation rate. Now, you may notice you didn't specify a ventilation rate, and that's because Zebra at this complexity level picks up a value of 30 cubic meters per person per hour, because that comes from a good air quality standard. So it's done for you. If you go into a different complexity level, you'll be able to adjust that value. So we've specified the air going into the building and leaving the building. It's a naturally ventilated building, so we don't need to do anything with fans and ductwork and everything like that. We now click on the incidental gains tab, and we've got to specify some idea of the likely gains from lighting, computers, charging mobile phones, who knows what, Xboxes, in this building. And we're going to use the default value suggested on the right of 1.1. But again, in this context, if you know more about energy use in Indian homes, you might well be able to specify a more realistic value. We now navigate to the space conditioning sheet. The ventilation strategy for the building is spread across the air, the space conditioning, and the systems tabs. And we realized this was probably not the best way of doing it, and in future versions of Zebra, we're going to bring that more together into a way that you'll find it easier, I hope, to describe your ventilation strategy. So if you've downloaded a more recent version of Zebra that we had yet to write when I did this recording, you're maybe faced with some information slightly differently presented on slightly different sheets. But in this case, the first beige box is heat recovery. We don't have a ventilation system with ducted air and heat recovery, so we don't put anything in there. And we don't have any fans, so the sum of the specific heat power is 0 for the fans. So we just leave that blank and go straight to the Systems tab. Again, after reading the pinky purpley areas, we have to start filling in some information here. At complexity level 1, there's limited information to fill in, but there are some important values. So the first thing to fill in is the domestic hot water demand. A lot of thermal models of buildings would leave this out, but then you'd only get an estimate of the cooling energy use of your building. And if you're trying to do an holistic design and drive towards zero carbon, that won't be very useful at all, because as we get more and more efficient buildings, you're needing less and less energy because of their insulation and air tightness. The percentage of the energy and carbon emissions from the building that's from domestic hot water and from plug use, etc., within the building starts to grow. So it's critical to include some information here. Now, we've got some suggested values there for the energy consumption of buildings. They were default values we found after research. They may not apply to the building you're designing in the location you're designing for. In these values here, which are given as examples, they're in per person per day usually. And that's actually the typical occupancy level of the building. It's not the mean occupancy level over a year on a 24-hour, 7 days a week, 365 days a year basis, but it's the typical number of people who are going to visit the building in a day. So it's not maybe its max value, but it's something close to that. In here, we're going to assume that there's 3 occupants a day in each apartment, and they'll want to use 3 people's worth of domestic hot water a day. Now, if you do a quick hand calculation, that'll tell you that you're going to be using 2,100 litres a day. Okay, we've assumed people use half the amount of hot water as they would in the dwellings suggest sensible value there, which come from the UK, because it's quite a hot climate, and in hotter climates, people have less demand for hot water. So the whole building uses 2,100 litres of that. How's it provided? Well, we're suggesting it's provided on the spot with storage. Now, when the building was finally built, it turns out, and we didn't know this, that it uses solar hot water on the roof, and but at this point we didn't know that, so we assumed that the roof had PV on the top, or in this design example might have PV on the top, and they'd use on-the-spot water heating. So we're specifying on-spot with storage. And going further down, we need to discuss the PV, because we think we're going to put PV. You don't need to put PV on the roof of a building in Zebra, but we try and encourage people to use PV whenever possible, or solar hot water. And in this case, we're going for PV, and we're going to say the total roof area of the building. Okay, this might that we might be able to put PV on. Now, this isn't the same necessary as the roof area, okay, because the roof area in the building is earlier on the roof sheet is the surface through which heat is lost. So if you've got a ridge style roof, you may have the insulation though on the horizontal plane above the ceiling, and it's that horizontal area which is the heat loss area, whereas now we've got this ridge roof, and we may only be able to use one side of that for PV. So this is the potential area for PV if we could just cover the whole thing that's facing in the right direction, or something equivalent to that. And that turns out, because we've got a horizontal roof, it is the same as the heat loss area, so it's 529. Stick that in. Now, you can't just cover a horizontal roof solidly in PV. Your PV is not likely to just be horizontal for one. It's likely to be in frames, inclined at a certain angle. And we don't know how much space is going to be needed to walk between the frames, etc. We don't know what else is on that roof to get in the way. But we're just going to say 60% of the roof can be used for PV. Now, that may sound a bit arbitrary, but the important thing to realize in any thermal model that whatever you can guesstimate as an input parameter is always going to be better than just leaving it as 0. People tend to think that, oh, we don't know something, that we'll just leave it as 0. But that 0 will be entered into the calculation. It doesn't matter whether it's Zebra or some other tool. So you are making a definite statement, whether you want to or not, about every single object that goes into the simulation engine or into the equations. So you're always better at doing your best and just guessing a number. So here, rather than saying 100% of the roof could be used for PV, we're just going to say 60%. We then go over to the right. And on your first use of Zebra, it's really important that you scroll around on each sheet within looking for this green area. Now there'll be at complexity level 1, there may be large area of blank green, and that's because there's either input data or results coming that you can only see at higher complexity levels. Okay, but you need to look around even in complexity level 1 to make sure there aren't any input cells or results that you've missed. And here we can see some input cells. Now we're going to do our space heating with electricity. So that's going to, we're going to do it through an air source heat pump. So that will have, or an air conditioning unit, an efficiency of 2. And it will run off electricity. Now the actual reality is this building doesn't have any heating demand at all. But for cooling it will have. And again, we've got a coefficient of performance of 2, and we're going to run it off electricity. The reason you have to choose the fuel type here is because the amount of carbon emitted per kilowatt of heat or cool depends on what fuel you're using. Domestic hot water, we're going to assume that comes off direct electrical heating at the moment. So it's got an efficiency of 1. And again, it's electricity. Okay, and that's it for our system sheet. We now turn to our embodied carbon sheet. Now, at the moment, the embodied carbon calculator within Zebra is extremely simple. You basically have a choice about using some default values, or you can go into proprietary software and actually work out the embodied carbon of your current construction. And the kind of information that will require is the mass of concrete, the mass of steel, the amount of glass. Any details you can find about clip-on facades, units, carpets, etc. And you can just go into other people's software and work out the embodied energy of your building and copy it over here at complexity level 3. But we don't know that at the moment, so we're just going to use benchmarks figures. And the main use of this is for us to get an idea of, if we want to create a zero carbon building, is the main problem likely to be the operational energy use, so cooling, lighting, etc., or are the majority of the emissions going to be coming from the concrete, etc.? And we need to focus on the embodied component rather than the operational component. So all we have is an apartment. Click. That's very easy. Okay. Construction type. Now, we just think this is going to be a concrete building, so we're not going to claim it's low impact. Okay. So we just click standard there. If we had said it was low impact, then we ask you to read these questions underneath. Okay, and write some comments. The text that you write there is not used in any way, but it's for reference for you, line managers, etc., to make sure that you just didn't tick low carbon without any justification, or that you're thinking of building a 14-story apartment block in southern India out of straw bale. Okay, so it's a logic check for everybody involved. And this spits out a default value of 850 kilograms of CO2 equivalent per meter squared of treated floor area. Okay, so every floor area, every meter squared of your building has embodied emissions associated with it of 850 kilograms of CO2 equivalent. Okay, that was all quite easy. And that's the end of the inputs. We have now got a complete model of our building, and we can turn to the summary sheet to look at our results, which is quite exciting, really. It's going to be our first model. Having entered all the data about the building, we turn to the summary sheet. There's nothing to input on this sheet, and you can tell that because it's not highlighted in red. So you don't need to describe anything else about your building. We've finished. And we can start looking at the summary results, and then we'll go back to the space conditioning tab to look at some more details, and then back to the Windows tab again to look at some more details of where this summary comes from. It's split into three areas, three tables. The first table contains nothing but the key design parameters. If you turn on complexity level 3, in this area here, you will see some other details about average U value of the building and things like that, which may be of use or not. And if you read the accompanying Word document to this video, you'll see those being discussed. But I'm going to move straight on to the next table, which is the operational intensity. So the energy demand, consumption, and primary energy demand of the building per meter squared of treated floor area. Now we've got a series of items listed in this column here. This is just talking about things that use energy that's supplied to the building. So we're not talking about, when it comes to ventilation, we're not talking about heat ingress through ventilation, okay, or cooling lost due to ventilation. This is only things that actually use energy within the building, within systems. So ventilation in this case means fan energy, and we don't have any fans. It's a naturally ventilated building, so they're going to be 0. We don't have any space heating because of where we are in the world, so that's 0. Then we come to space cooling. Now, Zebra calculates this building has a cooling energy demand of 25.8 kilowatt hours per meter squared of treated floor area per annum. That number will be different than the number that you'll find in the Word document, and that's because we actually made some slight different assumptions about the building in the Word document than we do in this video, but primarily about the G value of the glass. But we're going to work with the numbers that come out of the input cells that we've actually used in this video. So we've got 25.8 kilowatt hours per meter squared of cooling demand. You'll notice though that the consumption in the next column is half that. And the reason it's half that is we've got a coefficient of performance of our air conditioning units of 2. So our energy consumption is half that of the demand. So energy demand here is how much energy do we need to actually provide the amount of heating, to provide the amount of cooling. And then energy consumption includes the efficiency of that system, be it a gas boiler for heating or an air conditioning unit in this case. So we've got 12.9 kilowatt hours per meter squared of consumption. For domestic hot water, this is direct electric, so its efficiency is 1, so it's just 5.3 in this case. And the same is true of all the plug loads, lighting loads, and everything else in the building, which are summed up into these 9.6 kilowatt hours per meter squared. We see that the PV is generating 11.7, and it's shown as a minus because it's injection into the building rather than a demand from the building, and that's roughly the same as the energy consumption of the space cooling. So the PV is not making up the total energy consumption of the building, which would be 12.9 plus 5.3 plus 9.6, but it's making up kind of almost as enough to replace the space conditioning. So it's fairly successful, but not overly successful. And that isn't that surprising due to the fact that we've got a huge floor area, a lot of people in this building, and a very modest roof area, considering that. So if we now look at that information as fractions and in a chart form, we get this, and we can see that, for example, that the energy demand graph, the biggest item is this dark gray area, which is the space cooling. But when we look at consumption, there is a subtle change in, because of the coefficient of performance, that falls as a fraction overall. Please note that these add up to 100% in all cases, which is why this grey area here is larger than half of that height in the energy demand graph. In the next table, we find a little bit more detail we get a comparison to what we required in the first place. And if you remember back on the requirements tab, we set out our environmental philosophy, and we demanded that we had zero space heating. That's turned out to be true. We demanded that we had a cooling demand of no more than double that of the passive house requirement, so a total of 30 kilowatt hours per meter squared, and we're below that, so we're at 25.8. The primary energy is way below our goal of 240, so that's been fantastic. And our net primary energy, which includes the exports of the PV, comes to 35.8. The next figure is in red, and that's the net operational carbon. Now, the reason it's in red is we demanded a zero carbon building, but it's turned out the PV is not powerful enough to make up for all the energy use in the building. So we're not going to make that, and Zebra automatically highlights that in red. So if anything you match your environmental philosophy with, your design will be in black, and anything where you fail will be in red. The next table presents that information in the form of carbon rather than energy. So critical, as I said right at the beginning, will be the assumed lifetime of the building. If you assume this is 60 years, this building lasts for 60 years, then it can divide the embodied emissions by 60 to give an equivalent amount per annum, and then you can compare that to the operational carbon. So our embodied carbon is 850. It's in red because we were hoping for 500, but being we've taken no steps to use low embodied materials, we just chose the standard construction. It's not surprising we didn't make that requirement. And we can compare that number to the 131 kilograms of CO2 equivalent that the operational carbon adds up to over the 60 years. Okay, so years it takes operational carbon to match the upfront carbon is 389 years. We now return to the space conditioning sheet to see if we can find any additional information that might help drive the design through the next phase. We scroll down, we look at the space heating demand. There isn't any, so these numbers are not relevant or not useful in any way. So we go down to space cooling demand, and we find this heat balance graph. I'm just going to zoom in on that. Now, this is the heat balance, either during the heating season or the cooling season, is at the heart of what Zebra is trying to tell you. And it's initially quite a difficult thing to get your head around. I'd suggest if you've done a passive house course, you'll recognize this kind of stacked graph. It's exactly the same idea as passive house uses. By the cooling season and the heating season, or the cooling calculation and the heating calculation, there's a lot packed into that, and you've got to be kind of quite logical about it and think, what is Zebra trying to tell me? How does Zebra work? And we've written another document on this for those that want to look a little bit more into the detail of what these numbers really mean. But the first thing to point out is that Zebra doesn't actually know when the heating season is and when the cooling season is. There's nothing like that. It doesn't know a time of day. It's a mean monthly model. So it simply performs a calculation once a month and adds the results up. So, and it does the calculation very similar to the way PHPP does it, which is to look at all the gains and all the losses and make sure the losses balance with the gains at the set point chosen. So for the cooling calculation, it's doing that calculation using the cooling set point. And for the heating calculation, it's using the heating set point. So basically it just repeats the calculation twice with those two different set points. And with one of them, it assumes that you can add heat to the building to make sure that the gains and losses balance, and the other one, it says you can subtract heat by the use of cooling to make sure the gains equal the losses. Now in this case we're on cooling, and these are our results. Now if we look at the losses from the building, we can see that the building loses 21.1 kilowatt hours per meter squared of treated floor area per annum through the walls. So on average over the year, at a set point of 30, the building loses more heat through the walls than it gains through the walls. Now this doesn't tell you when in the year it does that or anything like that. It just performs the calculation for all 12 months, and it does it with that cooling set point. Other interesting things we can see from this graph is that another source of losses, and in the sense of cooling, losses are good, is the transmission through the glazing. We don't have double glazing. Now, if we were to rerun this calculation with a cooling set point of 26, and this is described in the Word document, you will see that these losses transfer into gains. Because with a much colder building, we're actually getting heat, more heat flowing into the building through the walls and through that glazing than we are heat going out through that path. Okay, so these results depend critically on the cooling set point. And that's an example of a parametric study worth doing. Let's see how the energy balance in the building changes with different set points. Other information we can see here is the 25.8 space cooling demand. And don't forget the actual electricity consumption is half of that because we've got a COP of 2, but this is the raw demand. In the right hand column we've got gains, and the two big gains we've got, we don't have particularly large amounts, we don't have heat coming through the walls or anything like that, because as we said it's already quite hot in the building because the set point's 30, and we've got incidental gains of 19 and glazing solar gains of 21. And if we want to reduce the cooling demand, we're going to have to tackle those two objects. So somehow we're either going to have to shade the windows more, use glass with a different G value, or we're going to have to convince people to use less electricity in the building, maybe A-rated, highly efficient electrical devices and lighting would be one example. On top of there, you can see a white area, 30 kilowatt hours per meter squared in the gain column. And if we look to the key on the right, that's non-useful losses, okay, which may seem strange because it's in the gains column for one. And what do we mean by non-useful losses? So that's the percentage of the losses. Oh, it's the amount of the losses as registered in the left-hand column that aren't useful in keeping the building cool. So, for example, you could have a situation at certain times of the year where the building is losing heat to the outside world, but there's no chance that the building is ever going to be warmer than the 30 and turn the cooling on. So the non-useful losses that are in the gains column, and the reason they're in the gains column is so these two histograms balance logically and numerically. So those losses aren't useful in reducing the cooling demand of the building. And we get the same thing happening if we were in a heating dominated climate, that you can imagine if there's already plenty of gains, incidental gains, etc., to keep them people and everything, to keep the building warm at a particular time of year, then extra solar gains, etc., aren't of any use at all. And they'd actually be reported as non-useful gains. Okay, so that's our heat balance graph. And if at any point you're confused by that, read the additional documentation. But you can see here the majority of the losses arise from the walls, the glazing transmission loss, the roof, and the infiltration. Now we're going to have a look over at the glazing tab. Here's the glazing tab. And the graphs in here take a little while to draw if you've got a slow machine. And we can see a lot of green area here. And some graphs which simply tell you the fraction of the sky that is visible through each window, their orientation, and the ratio between glass and non-glass in the windows. But if we turn very briefly over to complexity level 3 and return to glazing, we can see a lot of this green space is starting to be filled in with numbers. And this will allow you to look at the window energy balance on a monthly basis, which you may find useful in describing how your building's actually performing. So have a look for this extra information and you'll be able to find what time of year each window is a net benefit to the building and when it isn't a net benefit. And this is quite, the fact that these numbers are quite different from windows that point in different directions is actually a strong hint that maybe we'd be better off not modeling the whole building as one, but certain elements of the building, like the east-facing facades, east-facing apartments, and seeing how much energy they use, because we might want to actually think about the building differently on those different facades. And that's very common in architecture. If you're going to maximize energy saving, is to make sure that the components of the building that you use are chosen with respect to which way the building faces and how much shading it's got on different facades. I'm going to go back now to space conditioning, and we have complexity level 3 turned on. And we can see some additional information here. We can see the cooling energy demand on a monthly basis. So this is losses and gains through the building. And you can see there in the striped area, this is our space cooling demand. So this tells us when in the year we expect the air conditioning to be required. And we can look at that just from the windows as well. So we can, for each of the windows, window sets, sorry. I'll bring up the key so you can see the key. Okay, and we can look at the transmission losses and their gains. Okay, and see whether the window is of net benefit, which is normally a case in a heating environment, or a disbenefit because it's requiring a cooling load. Now, if we go, and there's a lot more detail in the Witten document that you may wish to study, but I'm quickly going to look at one situation. So we return very quickly to the summary, and our building has a cooling demand of 25.8 kilowatt hours per meter squared of treated floor area per annum. The question then is now, and it was one of the research questions we posed right at the beginning, and is described in the Word document. What happens if these occupants become more affluent and have the resources to cool their building to a set point that's far lower? They might not choose to do that. We're in a part of the world where people are used to very high temperatures, but there is a reasonable chance they will. And at the moment we have quite a low energy building, despite the fact it has little insulation. And the reason for that is it's in a warm environment, but not ridiculously hot. It's not in Saudi Arabia. So despite the fact the walls aren't insulated, the heat flowing through them is very low. And in fact, we just saw that actually the heat flowing out of those apartments is greater than the heat flowing into them when averaged throughout the whole year. So let's now imagine people have less financial constraint and decide to increase the air conditioning load by reducing the set point. So does the energy use of the building go up slightly? Does it go up greatly? That's the question we want to answer. So how robust is this building? I mean, it's got a 60-year lifespan. So we can assume that the occupants are going to become wealthier, or a different group of people might move into the apartment who are wealthier. So, and let's go back to requirements. And this requires you to be in not in complexity level 1. So you can see the cooling set point. And we're going to reduce that to 26, which is actually the default value within Zebra. If we do that and then shoot back to summary, we've gone from 25.8 to 104. Okay, that's quite a phenomenal jump. Now, the other way of seeing this is maybe people would, despite their income, would actually like 26. Okay, so this actually represents 26 Celsius. This represents a kind of desire or want and ambition, and that maybe we should be able to deliver 26 Celsius without this huge energy penalty. Okay, so we've basically the energy use has gone up by 4 times for that 4 Celsius change, and that's quite a phenomenal difference. It's going to make a huge difference to the fraction of incomes spent on this cooling demand. So we've now got this building using 104.5 kilowatt hours per meter squared of cooling demand. Obviously, the actual electrical consumption will be half of that, because we've still got a COP of 2. So what strategies could we use to get that number down and actually make these robust against an increase in wealth, but also better designed so that people with not the greatest income can afford to cool them to maybe levels that they might like to see? So first thing we do is go back to some of the U values. Okay, and we get a hint of why we might want to do that by now going to the space conditioning tab and re-looking at this space cooling demand balance. I mean, if you remember earlier, we had a load of losses. Now, those losses are transferred into gains. So the walls are actually pulling in heat from the outside world and causing the building to overheat. And if you remember, the only important gains that we had when we cooled to 30 were the solar gains and the incidental gains. Now they're actually smaller than the other gains, and that big dominant one is definitely U value of the walls. We've also other U values we can treat as a U value of the wall, of the roof, and the glazing transmission. So let's go and instigate some changes based on those things and see if we can bring this 104.5 of energy demand down. So, and this shows you, I think, how rapid you can model design alternatives and play games when you're in a design meeting as a group of people or in a studio lesson, and seeing what happens. So the ground floor is the purpley one, and that's small, so we're not going to add any extra insulation to the ground floor. That we can kind of conclude would be just a waste of money. So let's go to the roof, and this is going to have the biggest impact, isn't it, on the apartment that's adjacent to the roof, which could have a huge air conditioning load at the moment. And we're going to insulate the building. We're not going to go for passive house or anything particularly fantastic, but we're going to put an insulated layer in there, and you could look up ways of doing that within this context. But imagine we've done that and we can get to 0.35. And our thermal bridges, we're going to engineer those, going to consider engineering those better, but we pause for a moment and go, is it worth spending money in this area? And that's why we use our space conditioning tab. We go over there and we look at thermal bridges, which are pink, absolutely minute. So we can go, no, not going to treat my thermal bridges. Don't think that that important, be a waste of money. Okay. We go to walls. Point 3 into there. And we could look at the system, the summary sheet or the space conditioning sheet each time and see how we're changing things. But I want to get through the tutorial at a reasonable speed. So I'm going to drop into glazing. And I'm going to install double glazing. Okay, and as you'll see on the screen, there's a suggested default for the U-value 2. Okay, and there's also a suggested value there for the G value. And I've got complexity level 3 on, and you can see that a lot of dark brown cells have opened up rather than our light beige cells. And they're all the things visible at complexity level 3 and requiring input. But if you're just working at complexity level 1 but displaying complexity level 3, just go for those light beige cells. So we're going to have double glazing now. And we're going to put in 0.6 there for the G value because that second layer of glass stops a lot of light getting into the space. Okay, and now let's scuttle back to space conditioning. And we haven't quite managed to halve the space heating demand. We've got a long way down from 104. And if we look at the gains, what have we got that's large still? Well, we still got a problem with solar gains. We can't really do much with incidental. So maybe we can think about something we can do with solar gains to reduce that. We've also got infiltration and ventilation. Well, ventilation, we need the ventilation. So there's not a lot we can do that. But maybe we can think about a design which is somewhat more airtight. So let's tackle that infiltration. Imagine that we put strenuous effort into sealing every possible joint, particularly around window frames, door frames, junctions between walls, and things like that. And so let's try and halve that infiltration. Okay, and also imagine that the occupants can use some form of temporary shading during the hottest period of the day and the year to stop excessive sunlight coming into the space. So let's go to glazing. Go down to our statements about window sets, and let's imagine they included something equivalent to half the window when it was useful, each of the windows, but still let light in. But maybe when they're out of the building, they draw these blinds down, something like that. And we're just going to guesstimate that's equivalent to shading the window by half the amount whenever cooling is needed on average, because there'll be times when they're in the apartment and they want those blinds open, but whenever they go out they can close them. So we're going to put 0.5 into there. Okay, for air we're going to think about the infiltration of the building. So let's imagine we can get that down to 3. We're just going to change the text in there. So it's 5 times the pH passive house value, but we still think maybe that's realistic. Okay, let's flip back to space conditioning. Have a look at the graph. Still haven't managed to tackle some of the things we'd like to do. We still got a lot of solar gain through the glazing, though we've managed to reduce that. Okay, and we're down to 55. Now what we'd really like to tackle are those incidental gains, but there isn't anything we can do. If we flip back to glazing though, you can see that we made a mistake because we put the temporary shading into the heating column. So they're actually closing these blinds during the winter. That wasn't what we wanted to do. So we've learned a lesson there, and let's see what happens when we stick them in the correct places. So we go back to 0 there, or clear it. Now, when we look at the energy balance, we should see something quite dramatic. And that draws out the fact that you need to make sure whether you're trying to discuss heating or cooling separately with quite a few of the items, including this temporary shading. Now, we go to space conditioning. We're now down to 47. So we've certainly managed to halve the energy use of these buildings. Okay. Now, whether 47.8 is a low enough, small amount of energy, and don't forget we're dividing by 2 because of the coefficient of performance, for these people to afford. But we certainly made these buildings more robust against aspirations and wealth and what might happen within this city in the coming decades, and managed to control to some degree the carbon emissions of these buildings. Thank you very much for fighting your way to the end of this last video, and we hope you enjoy using Zebra in your own design work. Bye-bye. It's really easy to get locked into the idea that the low carbon story and the minimization of energy use is all that really matters at the moment in design. And there's some justification for that if you think about the climate emergency. However, even if the core of our philosophy is the reduction of harm via the reduction of energy use and carbon emissions, there are other things you need to consider to make the building just work for people. And some of them will probably help you reduce energy use anyway. I'll give you one example, that would be acoustics. If we just minimize for energy use, we're going to end up possibly in some climates, depends where you are in the world, with a sealed box. That's not going to be constructive for the occupants. It's not going to work in any kind of way. And actually, they'll sabotage some of your philosophy, possibly by forcing the opening windows that you had assumed closed or something like that. Another example would be just ventilation in general. Nothing to do with stopping noise getting into the building, but ventilation can bring in issues with air quality, etc. So there's a need to think about the acoustics, the ventilation, in the same way as you might think about the energy aspects. So thinking about the materials that you use, where you put certain components, like openings, and the sizing particularly of those objects. So not just thinking about ventilation in terms of red arrows and blue arrows and the direction of flow, but actually having that sized. So let's go through some aspects. So starting with acoustics. We've got this building design, it's fantastic. But one of the biggest problems we've got potentially is the building maybe in a noisy place. Maybe it's in the middle of Delhi or something. And what are we going to do with that traffic noise? Obvious strategies would be to put the main openings of the building on the facade away from the main road. Okay, that's brilliant in the sense that it's not only going to reduce noise ingress, but it's also going to reduce probably pollution ingress from those vehicles. However, that'll only work if there's a path for air to go into the occupied spaces. So we've got to think about which direction the wind would be coming from, and work with that as well to size openings, place openings in suitable ways. Really think about what's driving the ventilation pathway. Is it temperature difference? Is it buoyancy? And having an understanding of those. Maybe creating a little spreadsheet would be useful with the standard CIBSE equations or equivalent. There's a document called AM10, which will be really helpful for that. So look up CIBSE AM10. Then when we get into the building, what are we going to do with this cool air? Obviously, we want to produce good air quality, but we've also got to think about, can we use it for cooling? And at what time of day is it occurring? Do we want a low mass building? which responds very quickly to the outside temperatures, or do we want a high mass building, which responds more slowly? And it's not obvious which of those you'd want. And somewhere like Delhi is going to be very different than somewhere towards the Afghan border. It's going to be a very, very different situation, or the Pakistan border, because of the diurnal cycle. And it's quite easy to create a high mass building, which you think, oh, that's going to reduce temperatures, and it won't respond so quickly. But you could stick it in southern India, and you'd find the opposite effect, that you actually wanted a more perforated building, a more responsive building, because there's virtually no diurnal cycle. So really think about, in a holistic way, how you're going to connect the acoustic story with the ventilation story, with the energy and carbon story, okay? And have a strategy and talk to your client about that, okay? Air pollution can come from vehicles, therefore localized, but it can also be just general pollution around the whole city. For example, in Delhi, very well experienced with the crop burning story, okay? So think about that. Think about how you can bring in the right quantity of air, because if you're going to have an opening for air to flow into, the larger that opening, the more ingress of noise you're going to have. So people need to open windows, for example, or any other opening system, only to the point that provides the air quality. And is the air being provided for air quality, or do you need much more for cooling or something like that? What actually is what air do you need, and how much do you need of it? So you can't just have random openings. So one example of that would be, if you're an architect and you're having a difficulty sizing an opening, go and get the equations, or go and get a civil engineer or someone who can help you with that. Because if you're struggling with the sizing of openings to provide a certain amount of air for good air quality, what's the occupant meant to do? The occupant's not going to open Excel and run a calculation of how far she should open that window, and probably won't understand, quite possibly won't understand, that opening a window on one side of the room and another side of the room to provide cross ventilation provides a lot more air. Or if they do understand that it does provide more air, are they thinking that therefore they could reduce the size of each of those openings and therefore improve the acoustic environment? So I'll just go over that again. In a cross-ventilated situation, cross-ventilation is so much more powerful usually than single-sided ventilation. The corollary of that is that you can open the windows to a much more modest angle and use cross-ventilation to provide the same amount of air. And if you do that, you will actually improve the acoustic environment as far as sound ingresses from the outside. And there's other tricks on other topics. Okay, but the main thing is to think in a holistic way and use some form of sizing calculation, possibly with support from others, to think about the actual size of openings. Another example would be stack ventilation. Stack ventilation is driven by the height difference between the ingress, the opening, and the outgress. Now, the further they're apart, the more air will flow. And therefore, just the same as we said with cross ventilation, you can have smaller openings if you've got a more effective stack difference. That's difference in height. So you could bring air in on the ground floor and export it up on the roof, would be a classic example of that. And therefore the openings on the facade itself can be much smaller low down. Low down is probably where the greatest amount of traffic noise is. So think in this holistic way, come up with a story for air quality, ventilation and acoustics that works rather than imposes your carbon story. Thank you very much.